This one, are you ready? It's not. That was from, that's a whole over. Y'all don't need part of that. I'll scratch it out. No, do what? Oh, did it start? Yeah, no, I'll go over it. We believe that this is where we were on Monday. Is this correct? Y'all feel caught up at this point? Like we could just jump right in right here? Maybe? You think? Not sure. Not sure face. Is that a not sure face? That's a not sure face. Okay. So let's think back. What's going on? What are we on about here? What's this about? What's our point here? Okay. Yeah, we're going to use ice tables because we know that equilibrium ratio, so we know what KEQ is. In this case, KEQ is 54.3. And remember, y'all, no units on these, and they can be such incredibly wide range of values. We could have, here we've got 54.3, right? But you could easily have 1.234 times 10 to the 14th, right? That happens all the time. Actually, you see 14th a lot. You could have 10 to the negative 25th, right? It doesn't matter. These can be extremely small values, extremely large values, or anything else, okay? So don't be gone off and you're like, should I be calculating something with 25 zeros on it? Yeah, maybe. Okay. You said it involves a what, Sydney? Ice table. Can y'all start with setting up an ice table here? Like, what do I like to put at the top of mine? You don't have to do yours the same way, but like, what do I put at the top of my ice table? A lot of people will like put a header with a H2 and then an I2 and an HI, but I actually just write the balanced chemical equation as the header to my table. Does that make any sense? So I think it cleans it up a lot because you're going to need that thing balanced anyway. So I just put that as my H2. Oh, there's one of those, right? It's balanced. I guess we already balanced this last time. I hope so. You should always check, make sure it is. Somebody told me that a lot of the struggle is reading the questions and figuring out what do I need to do? How do I problem solve this? How do I try to set this thing up in the first place? It's not, it's not that the math is not a struggle. I don't mean to say that, but I think that also a struggle is setting it up. So let's talk through setting it up here explicitly. What do we want to do here? What's our icicle is just kind of a tool. It's made up. It's just a little algorithm that helps you do things. What could we do here to set up an ice table? Marcy, what is an ice table? Okay, so let me put that. Let me put an I for our initial, okay? And then change, which I tend to do with this delta, right? And then what? And what the concentrations will be at equilibrium, okay? So what do we know in this scenario here?
Start with 0.5 and go to H2.
Yes, but I wanted to look at the units. You're correct, Marcy. But in this case, I don't want to be misleading. You only start with 0.5 here because it's 0.5 moles in 1 liter, making it a concentration of 0.5 molar. You want it to be in molar, okay? In this case, numerically, it's the same as the mole because we're in 1 liter. I just wanted to make sure to specify that we really should be working in molar, right? Okay, so you wanted to say what, Mercy? Then you start where?
0.5 moles of H2 and I2.
Okay, I'm going to agree with that, but I want to ask, what about the HI? Okay, and I think that's a piece of this, is looking at it and reading, why does she want to start with 0 for HI? I agree with her, but how is she getting that from this question set? Say again? Hasn't reacted yet, okay? And a lot of times we will have these that will have some product in there to start with too, okay? But you can look at the problem and see, is it trying to imply that there's 0 product? In this case, it is trying to imply that there's 0 product to start with, okay? Okay, now that's an important piece of building this table. Important enough that I will probably ask you test questions on building this piece of the table. What goes in the change side? That's the equilibrium, right? What goes in the change? Minus X. Uh-oh. Oh, the bravery has evaporated a little bit. Come on, be brave. What about it? Plus or minus? Plus, good. All right, tell me, Sarah, tell me your logic to get there. Talk it through. It is correct, so talk it through.
I'm talking about
That's okay.
gaining.
Okay, it's gaining. It's a product. It's being produced. Okay, what else? So it's going to be positive. Okay, and why 2? Okay, because of the balancing affair. And so, if stoichiometry says if you lose one of these, you've got to gain 2 of these. Okay, so that piece is still based on the stoichiometry from Chem1. All right, now, Brandon, what were you saying would go in the equilibrium here? Okay, 0.5 minus X. Okay. 0 plus 2X or just 2X to make it easier in your equation. Speaking of that equation, what do I need to set up? Okay.
Concentration of HI squared over concentration.
Okay. Now what?
You know that at equilibrium constitutes 4.3.
Okay. So we can just say, yeah. All right. Now what?
It's going to 2x squared over.
Okay. So yeah. So what am I going to plug in next? Marion, what do you want to plug in where?
So like for HI, you would get it from your equilibrium on 2x.
Well, it's 2x, it goes in there, and then it gets squared, right? So, I think you left out a piece of what you were saying, right? Because there's a trick that I still want to point out here, okay? All right, and then what am I gonna put in for H2?
You either do separate or just put them both.
Yeah, you can. I don't want to skip steps yet, okay? I want to do it all the steps to start with. We'll start skipping steps when we get used to it, okay? Right? So what do we have? So we've got so we've got, get up here in the light so everybody can see it. H4.3 equals, I'm going to plug in my stuff here on top, inside that bracket, inside the bracket, I've got 2x. And I think that's important to point out because it's the 2x that gets squared, right? So the numerator is not going to be 2x squared, it's going to be 4x squared. The 2 gets squared also, and that's important, okay? See where I got all the pieces? Yes? Okay? All right. Ignore the left side of the board. Okay? What math class are you in? All right. Ignoring the left side of the board, what would you do? Who do you have for guys? I don't know what Sebagala's big focus is, but I'm hearing Vince Parcell down the hall yelling about factoring, right? Yes? Yes, okay. So, but kind of unfactoring here so you can see if somebody has factored this out. Where does this go? What do you do with this? What would you do in math class? Ignoring the left side of the board. The chemistry doesn't exist right now, only the math. What would you do? Like this in the light right here on the board. This is the only problem that we have right now. What would you want to do? Okay, I'll do that. Let me do that. Like this? Okay, fine. Now what would you do? Lori? Okay, when you do that, I thought they got rid of the word. I mean, they taught me foil, but I thought they beat math teachers up in high school for using the term now. Double distributive was supposed to be the new thing. Yes, yes. So what would you do? Let's see, let me do a little sub problem here. 0.5 minus x times 0.5 minus x, right? So you got 0.25 minus 0.5x minus 0.5 x plus x2, right? So we've got x squared minus x plus 0.25 for the bottom. Yes, all right, so let me put that in. So now we've got, let's see, 54.3 equals 4x2 on top over x2 plus x plus 0.25. Yeah, happiness so far? Remember, we're ignoring the chemistry. We're just going to do the algebra right now, right? Okay, now what? What would you do? All right, cool. All right, I'm going to do that. Do this for a second. So if I multiply both sides by the denominator, right? I just can't. It's good. Okay. Over here, though, what's going to happen? What are you going to need to do? Yes. Okay, I'm going to do that. I'm going to get 54.3 x2 plus 54.3 x plus, somebody help me, please. Oh, wait. Which one's minus?
X. It's supposed to be x squared plus.
The linear term is negative?
Yes.
Okay, thank you. Okay, cool, thank you. What's my C term?
13.
Okay, still equal 4x2. All right, now let's assume that we don't have solvers to work with yet. We got to use the quadratic. What am I going to need to do to be able to use the quadratic here? Why do I have to do that? Because I have to set it equal 0 and it's set equal 4x2 right now. Subtract 4x2 from both sides. Right? So I got 5, 0.3x 2 minus 5, 4.3x plus 13.575 equals 0. Yeah? Yeah? Okay, well now, I can label this, you like to label these as your A. Oh. Make sure, this is going to matter. Make that plus negative, right? That's going to matter. Just put it in a negative value for your B. Yeah? Make sense? So far, so good? All right, everybody run the quadratic. Tell me what your x equals. What is the quadratic formula? For a, x squared plus bx plus c, x equals. Make sure I get this right, y'all. Doing it from memory, always dangerous. Is that correct?
Yes.
Okay, all right, dude. Plug it in there. Make sure you're practicing with your brand new calculator right here. So making sure that you're practicing, and I suggest heavy usage of your parentheses. Okay? Plug it in there, and I'm going to go cheat. Download my Excel calculator. It's not really cheating since I wrote the Excel calculator. So, yeah, you could use Solver. Yes.
Yeah, you should get to the next one. The whole positives.
Oh, then you have to, not that one.
Oh, yeah, I know the trick though.
Okay, what is it?
One that is greater than our maximum.
Ah, yes, that's the deal, right? So we're going to look and see. Well, let's all walk through it first before we spoil it for everybody, okay? Now, I don't remember where I stuck my quadratic calculator.
You should get to it.
Go download this thing.
Turn it over. This will be a rehash. This will be a rehash. Intercept. Intercept.
Yeah, you got to figure out the solver for your own individual calculator if you're going to use it.
Oh, I just want to figure it out.
Yeah. Oh, you're trying to figure his out? Yeah, you can do the graph. What did we have? A equals 50.3. B is negative 54.3, and C is 13.575. Good. Quadratic spit a thing out. Some calculators you can program the quadratic formula in ahead of time. That might make it easier for you, less mistakes to make later, right? Yours has got all the fancy things. You're using the fancy or not?
Oh, I was solve population.
You already have your answer, right? Try. Oh, slow. And so you actually have the advantage of you can start just like this. You don't have to solve it for zero. Put 54.3 in that first box. Okay, in the second box, put, you want to put an extra parentheses around this. Put parentheses 2x squared, put that in parentheses. Makes sense?
Yeah,
No?
I think so.
Parentheses. Should add. Parentheses, square it. Open up parentheses and divide. Put a parentheses around the bottom. So yeah. And then parentheses, 0.5 minus x, close parentheses. Parentheses, 0.5 minus x, Says once we get, right? 3 point what?
3.68.
Check something. Something's not.
I got it right when I just put it in.
Okay, maybe we can go with that. I'll have to check your solver later. Okay? Don't lose that, okay? Don't just clear your memory later. We'll check it. What's on get? 2 answers? You have 2 answers correct, yes? Yes? Everybody got 2 answers correct? Okay, unfortunately though, so that was our x equals, what did we get? X equals, I'm gonna put it over here, so we're gonna need it over here. X equals 0.686, or x equals 0.393. Yeah? Happiness? Oh, wait. Oh, and tell me, Scally face. Yeah, this is the reason you gotta practice the quadratic, right? It's a little bitty slip. Yeah. You gotta be very careful. Yeah, what'd you get?
1.77.
Okay.
I put like, I always have like parentheses.
Where did you put your parentheses?
Chocolate.
Okay, I tell you what, here, I'll do this for you. Do this, we'll do this. So you put it in as negative 54.3, right? Plus minus root negative 54.3 squared minus 4 times 50.3 times 13.575. Do you have to do this, Brady? Do you have to get people to try to think in the math lab? No?
Some people, yes. Some people are good enough to science.
All right. Yeah. Kara, let's do it. Let's actually write them out step by step. Write out each step. I know it's long, but it's better than losing the points on these things. So write this step out, plug them in. Okay? And what do you do first? No. No. Calculator's only going to help you a little bit at a time. Write it down. Write this down with it plugged in.
Is the bottom supposed to be the
Yep, thank you, ma'am. Positive, isn't it? So write them down, and then what should we do first? Where do we zoom in first?
Like outside of the square root, make that possible.
Okay, that's fine. You can do that. What else? What next?
So negative 4.3 squared.
Okay, so let me just do that step. I'm trying to get you to write all these down. So positive 54.3 plus minus root. Okay. What is negative 54.3 quantity squared?
2,948.29.
All right. Minus, how about 4 times that?
Negative 4 times 50.3, and that would be negative 2,731.
To what?
2,731.
Okay. All right. All under root over 2 times this. Right? Okay. Now what would you do next? Yeah? Yes, so far? Yeah? You're not sure? Now what do I need to do? I need to bifurcate now, right? Because I need to do my plus and I also need to do my minus on the top. What if you do your plus on the top? What do you got? I guess you do square root first. Also, I wonder how many people on my exams would miss because of the quadratic itself. And then this exam 2 and also exam 3, because we're going to be doing it there too with the H's. True that. Right, that's true. Yeah. What would you do? What would you do to get a lot of extra or a lot of partial credit? Yeah. So I can look for partial. Right.
Okay, now I'm getting it.
Okay. Did you find where your error was?
So I was putting all of it on one, instead of just breaking it down.
What's the 54.3 plus square root of that?
That is, 695.0%. Not that, would be 0.68.
And this time?
Trying out to 39.56. The 0.313.
All right, dude. Okay, now we've got our 2 answers here, right? Okay, now I gotta go, now we've done our math, now I gotta go back to the chemistry. If I don't need that board again, we should just leave that back there for a bit. Okay, so now what do we do? We have that, what do we do with it? Plug it into X, okay? So what happens if we try to plug this one into our first X? Okay, does negative concentration have a meaning? No. If you have negative 0.186 molar concentration in your beaker, does that mean you stole some of his? No, I guess it means you stole some of yours, right? I don't know, right? So, but you can't have a negative concentration. Does that make sense? Now, you can have a negative X. Please don't always discard your negative answer in the quadratic. Not true. Sometimes you may have set this thing up backwards and the negative X has meaning. Okay? But you cannot have a negative concentration. That's not a possible situation. Okay? Make sense? Now, there can be little tricky situations where so if you get an answer that says negative super duper tiny concentration, okay, that might just mean essentially 0. Okay, so negative 1 times 10 to the negative 25th or something, or yeah, something like that, that might be essentially 0. So that might be what you saw before accident. Okay, all right. So if this one gets a negative, we're going to get rid of it because no neg concentrations, right? So we got rid of that one. Leaving the other one, how does it answer the question? Concentration of H2 at equilibrium is going to be what? I agree. 0.107 moles in that stainless, in that 1 liter stainless steel flask for H2. Also, in this case, because of the math particulars of this one, turns out it's the same answer for I2. But what's the concentration of HI in this flask? Yep. 0.78. Beautiful. Make sense, y'all? Yes? Owen, talk to you.
I'm still trying to figure out how to put it in my calculator and I don't know wrong here.
You write out all the pieces.
Like, what's that square right there? How are you taking the square? What are you doing to get square?
What you see is positive and B is it may have been your original house. Hold on, let me roll the screen back up. Roll the screen back up for a second, for when y'all. Well, I think this is a practicing the algebra side. Let's see. We got a negative for B and a positive for C. Want to get a picture of this for you later? And you can come back and like deconstruct your algebra. Does that make sense? Okay. Got it? Okay. Yeah. A lot of ways we do it. One of the things that's kind of coding is that if I say H2 concentration, equilibrium, or you can say final, or something like that, equals, let's see, 0. What did you say it was, Miriam? 107? Also, And remember two times, right? The 0 dot, what is it, 7? Let's see, I would go back and check. Let's see, 3, I could probably have 3, 6. Okay, that help? Is that what you're asking?
Yeah, and I just wanted to discuss.
Yeah, although technically, it says calculated concentration, so molar is the right answer here. Technically, the way this one is set up, if you put 0.107 moles, also correct, but only in this case because we're dealing with a 1 liter. Okay, don't guarantee that moles and molar is always equal. That's only the case if you're dealing with 1 liters. Okay.
I initially had the negatives incorrect way,
Uh-huh.
fucked up by accident.
Okay, so back to Lect. Lect says, if a system is at equilibrium, right, and you do something to perturb, which is word I think, perturb that equilibrium, then it will shift to try to restore the equilibrium as much as possible. So, if you change the Q, then the Q, whichever direction you did change the Q, it will try to shift back towards equilibrium, okay? To try to reestablish the Q to K. Well, that means adding or removing a reactant or a product. Sometimes it can involve changing the pressure, okay, but the only time changing the pressure, theoretically, helps is if you're using gas phase components, either products or reactants. If any of your products or reactants are gas phase, now pressure matters, okay, because you're using partial pressure for those things. Changing the temperature will, in fact, change the equilibrium. Now let's think about that for a second. How did we start out equilibrium? I had those orange and blue curves relating back to our kinetics, first part of the chapter, right? What were those orange and blue curves? They were showing what? Yep, and then we could take a derivative and find a rate, right? And so what would happen if you change the rate? Well, if you change the rate of the forward reaction, right, then you're going to shift the equilibrium. Change the rate of the backwards reaction, you're going to shift the equilibrium. They won't change at the same, probably won't change the same. So you're going to change where those lines, where those asymptotes, those horizontal asymptotes, where they end up being relative to each other in that equilibrium ratio by changing the temperature, because you're changing the speed of both the forward and the backward reaction. I'm not doing this as an online question anymore. I used to do this as an online question. That website up there was beautiful. They let me use it for up to 60 students for free. Put in my own questions, export them in Excel. It was great. And then suddenly, one semester, they're like, you can continue to use Socrative for the low price of $500 a semester. That's how the world works, right? So I'm not using them anymore, unfortunately. But anyway, you would answer this how? What would you put in for what I have labeled as Q4? What would you put in if I were using this as an online clicker question? So adding N2O4, why will it cause Q to be greater than K? Where does the N2O4 go in the calculation? On bottom. Now let's look at that for a second. If we take, it's going to make a fraction, right? So let's say, what's my random fraction going to be? Right?
5%.
5/7. Okay. I'm gonna add 1 to the denominator, okay? Actually, 5/7, afraid I like it, it makes sense to me, but I'm gonna use it easier. Because I wanna make sure everybody follows me in fractions are bad words. Let's use 3/4. I think it'll be easier. Can y'all picture 3/4, 3/4? Like you got 3/4 tank of gas. Okay? Yes? Let's add 4 to the denominator. Right? What happens? I agree. That's a smaller amount. Does that make sense? Okay, so let's go back. Adding into a 4, where does it add to? Adds to the denominator, which is going to make Q. What's going to cause to happen to Q? Q is going to go up or down? Down. It's a smaller value. Okay. Well then, if Q becomes smaller, then what does it need to do in order to catch back up to K? Okay, so what's going to go down and what's going to go up concentration wise? In this case, I have temporarily caused Q to shrink, right? So Q is small. Now, what does it want to do? More numerators and by taking from the denominator. Therefore, it's going to shift, right, to the right. Shift towards right. Yes? Does that help? What? Make more numerators. I kind of like it. Make more numerators. Okay, let's go to question 6. Adding NO2, what happens? Well, that's true, but that's Q7. Well, no, I think I know what you're saying. Say it again. Q goes up. The Q value became too large. So what's going to happen? Make more. Okay, yes, make more denominators. Yes. Right? Does that make sense? Y'all? Yeah? All right. Even if you add this with only adding part of a reactant for a problem. Okay? So let's say we have let me think of a good one here. Let's do I'm trying to think of an example that does not involve H+. So I'm trying to stay out of the acids. That makes it harder to think of a good example. Did we do some with PB leads? Let's just do would you look up for me KF of PBI2? Right? I just want to use a bad number. And I'm not ready to tell them KSD yet, that's coming in a minute, but I don't want to jump ahead. I'm just couple of, errors. Do what? That sounds right. 8.what? 889. Okay. Would somebody flip that over for me? Would somebody take that and raise it to the -1 power, please? Or just do one over that? Fabulous. Good. 2.4 E3 right here. Beta is 1.4 E3. So 1.4, somebody do this for me. Put it in parentheses, 1.4 E positive 3, raise that to the -1 power. (1.4 E positive 3 and raise that whole thing to the -1 power. 1.4 E
7.14 E -4.
7.14 E -4. That sounds right. Is it close to what you've done? No. All right, let's go with this now. Okay, so this is our equilibrium situation. Okay. Yes? You follow? Okay. New problem. We've not seen this problem before. We're going to start with some random amounts of stuff. Okay? All right. Our random amounts of stuff, initial PBI2 AQ, and it's important that this is aqueous, equals what concentration, Miriam? 0.7 molar. Okay. All right, cool. Merv, what is my initial concentration of BB2, of lead 2 plus AQ? Just making it up. So I don't know the answer to this problem yet because they're making it up. What's that again? 0.3 molar. All right, cool. All right. So Braden, what is my initial concentration of lead 1 minus?
That's
0.2 molar. All right, cool. Well, what is our equilibrium concentration? Let's go. Now this one, the math is going to get harder here, okay? I'm just trying to show you where this really goes. I am not going to give you one this difficult on the exam, right? So you know if you can wrestle this one, this is going to be harder than one that's on the exam. Okay? What is my K? Well, I guess let's do the ice table first, right? PBI2 goes to PB2 plus I2 I minus. What would you like the ice table to look like to start with? Do as much as you can, hand off. Says her initial line. Oh, it's going to dry. Initial change, equilibrium. You can use the C. Oh, equilibrium on the bottom. And that's ice. If that helps, use the CICE, initial change, equilibrium. So it's kind of an ice table. Okay. All right, cool. Can you fill anything in, or do you want to hand off now? Hand it off, somebody then. Get somebody to take it. Mercy will take it. Those are initial. I'll put it. That little zero, remember, means initial. Okay? Good, good, good. Now what? Okay, y'all see me plus x and plus 2x there, right? Okay, really different than what we did before, isn't it? Yes? You want the next piece, you're going to hand it out. Oh, coming from Miriam. All right, Miriam. What's that equilibrium line look like, lady? (0.7 minus x? 0.3 plus x. Very good, very good, very good. Okay? And 0.2 plus 2x. All right, now it's about to get a little bit difficult, right? So, we're not going to give it to Braden yet, though. We're going to give it to Braden after it gets actually difficult. Okay? Braden, get ahead of us. So you can do some algebra for me.
Should I do like
Yeah, KEQ, right, equals what? What's our setup? You don't have to put numbers in, yeah. What's our setup? KEQ equals what over what? I minus, I agree with I minus. No, not the 2. Okay, good. All right, the 2 doesn't go in this, but the 2x is the concentration value for the I. But it's just I minus. Don't multiply your concentration by 2. But it does get squared. Good. Good. You got your head of you now? You getting there? Go, there you go. All right, beautiful. Do you want to plug in the expressions there before we end it off the break? It's gonna, yeah, I know.
Get that calculator working.
Yeah. But I'm not gonna give you one with it. This is gonna have a cubic or a, no, it's gonna have a power 4, isn't it? I'm not gonna give you one of those in anything.
That should be.
Is it?
Yeah.
All right, beautiful. All right, Braden, you're up right here. So 0.2 plus x times 0.3 plus x all over. This is 2x. Yeah. This, wait, which one is 2x? One is squared, right? Yeah.
Can we go over there or?
Now, come here where we're on video. All right, y'all. Then you get ugly. Because what happens here? What do you have to do with the algebra? All that algebra that they tried to pound into your head in high school, here's why, right now, right here. So if your little sister, little cousin, is ever in algebra class, and they're like, when am I ever going to need this? Remember, I know this guy, call it right now. Okay? All right.
Minus 0.7 minus x.
So you multiply by the denominator first, right? He's going to have to distribute that in a minute. Equals.
Pull that out.
So you're going to do the square part first?
Okay. 4x squared. Easy part.
I get 0.8x, if you agree, plus 0.8x. And then plus
No.
0.04.
Yeah, 0.04.
0.04, yeah.
That's what I do.
And we still have to multiply by the 0.3 plus x. What's the 3x?
I combine both.
No, 0.3 plus x, and it's, yeah. Yeah, that's why it's got, okay, now it's gonna get more complicated. You're gonna factor that guy through, right? Not factor, reverse the factor, what that is.
I'm just gonna go for this part for now, because I was gonna.
Yeah, we'll come back to that, yeah.
Works.
Wait. Yeah, oh, you're doing, okay, you did the x first. Go ahead. So, one thing, y'all, that I know that a lot of times you don't do it in math class, but I strongly recommend that instead of 0.8, that you start to write 0.8, because a little dot is easy to lose in your calculations, but if you've got 0.8, it's more of a mental cue. Why did I put that 0? Oh, there's a decimal. Okay.
So all those to be a 4x cube. Ready to get
0.8 plus 0.8x squared, 0.8. I know, okay, 0.04.
Okay.
0.4x, okay, and then you do 100.
Yes, we're starting on the 1.3 there.
So I put in the x squared term. So that is going to be 1.2 x2
Plus,
0.24 0.
I used to not be the fastest. And then 0.012.
0.2.
0.
Wait, 0, 0. Wait. So 1, 2, right? With 1, 2, 3. Yeah, you're right. Okay,
And we're gonna go ahead and just
add them up.
add those down. Get 4x cubed plus. Plus 4. Equals sunscreen.
Okay. Somebody help me. 7, 0.7 times 7.14 e neg 4. Somebody help me, please. Come on, our mental math's getting tired, y'all, please. 0.7 times 7.14 e neg 4.
4.998 e to the negative 4.
We're gonna call 5.
Okay, yeah,
5.
That's fine, you're probably close enough.
Minus. And we're gonna go ahead. First, we use those over to this side. So we're gonna get minus 5, 0, e neg 4 plus 7.14 e neg 4x. So now we're gonna add over to this side. Somebody add those two. Yeah, I know I'm writing them, so just.
Oh, you're gonna set it equals 0. Okay.
Oh, you want me to go that way?
I don't care.
I think this will be easier.
I believe you. You're the math people. I'm not a math people.
Because then some of you are probably over or worse than source. I'll try to figure out the rules versus that.
No, you're gonna finish this line and we're gonna go to the computers. All right.
Because this would be painful.
It will be, I agree, it would be very kind. Yes. There, just like the quadratic, there is a cubic formula also.
You already used it.
Yeah, but it's years. Yeah, it's very tedious. Nobody uses it. Everybody just goes to solvers.
Oh, wait. I messed up.
Y'all help me. Help me. Good man. Beautiful. so it needs to see the E starts. That looks right. Yep, that's right.
And that one.
0.01205. Yep. Yeah, good. All right. All right. So then you can go through a table process to solve the quadratic, or please note what I have typed in up here. Let me zoom it in for you a little bit so you can see. All right. If you don't know Wolfram alpha, Brady, do you use Wolfram?
Actually, I don't know which one it is.
This one is a beautiful solver. And the part that I'm going to talk about is free. There are other pieces on this that you can pay for, which I legit not worth it. But this part's free. So you see what I typed in here? This is our original. This is Miriam's equation right here. See this? This blue. That's what I typed in to the input line. Okay? You gotta be careful in parentheses, but you can just type this into your input line. Like if you're solving this for homework or for lab calculations especially, right? So if you're solving this for lab calculations later, use the Wolfram or something, okay? All right, and you type it in, and enter, it's gonna go away and calculate for a little while. We have 3 answers at least, is that right? Yeah. Solutions that he came up with. What do you notice about those 3 solutions? They're all negative. What does that tell you about our initial setup? Oh. What does it tell you? Huh?
Renegade reactive.
Yes, this is going to run backwards, right? Because all the answers are negative. Now, which answer is the correct one? Huh. What do you think? Which is probably going to be correct? If I say for, let's look at the I concentration, right? So our initial I concentration is 2 molar, right? Plus 2 times negative 0.2, or 0.3, right? Is that going to work? 0.2 plus 2 times negative 0.3 is going to be a negative concentration. That ain't going to work, right? So the first one is not the correct answer. Does that make sense? Period. Yes, maybe. I want to try to let you lose you because there's a lot of little numbers. Huh? Okay. So our initial concentration was 0.2 molar, right? If I take the first answer there, x equals 0.29, right? I say this plus 2 times negative 0.29, right? What does that give me? I want you to calculate. 0.2 plus 2 times that first answer right here. What's it give you? Okay, 0.5. No, not a real thing. That one's off the list. That's not our answer. Okay, let's take the next one. Does it work? That would work. It worked, Kara? So 0.2 plus 2 times this negative value right here gives you what? Also negative? Oh no, it's not that one either. Let's try that first. Oh, okay. So now you think you can solve it? So now can you help me then, everybody, how would, like Alice was saying a while ago, right? What do you want to do? You want to write your final, right? So Yeah, we're fine. Equals what? What's that? Come on, y'all. Let's check this. Put them to work.
I'm trying to work something out.
You do know how to solve it? Yeah, I mean, so one of the things that happens is over here in y'all's side of the house at math, right? The numbers are nicer, right? Right? Like chemistry is algebra with equal coefficients. Okay, so
Have to do all units, my whole life is quite local life. I've run some big division law to try to get one. Things that you can find one successful in quadratic formula.
oh, right. You can,
Because then you would have.
because you can factor out an X. No, you can't factor out an X here.
No, we got, I was saying that once you do some big division, once you do a rational root, that actually goes to zero. Which, good luck.
Okay.
You could actually-
Yes, Cindy?
First one is 0.775. And 0.225. 0.05.
Y'all happy with this? Brayden, do you want to picture your work before I get rid of it? I need that workspace. Blue, need blue. All right. Good. Everybody? All right. So, we have found our equilibrium concentrations, right? What would happen? What would happen now if I got my beaker all set up in the lab, I'm happy, let it run, got these equilibrium concentrations, I turn my back and Allison's like, right? And she puts in to my beaker enough moles to cause, let's say we're working in 1 liter, right? My beaker is 1 liter. That'll make our math easier, right? And Allison drops in 0.1 mole of PbCl2. Right? Oh, wait, that's not a reaction, right? Our reaction was about lead iodide, right? So this doesn't matter. You agree? Do you agree?
Yes.
You do. Do you agree? Okay, our reaction was lead iodide, right? The black here was lead iodide. And Allison just poisoned my reaction with lead chloride. So that doesn't matter, right? It's not lead iodide. So it doesn't matter, right? Oh, really? Why? And which part of that matters? Only one part of that matters. The PB. Okay, very, very good. Okay, even though it's not our reaction, it's not lead iodide, it is lead, which is part of, right? Part of our system. You agree? So what's it going to do? It's going to increase the PB temporarily, but in the long term, that's going to come back down and do what did you say? It's going to run backwards. Agree? Yes? That makes sense? All right, cool. I'm going to leave it there for a second. I want to get to solubility before you leave. So, we find this situation right here. Now, I specified that this system up here was about PbI2 aqueous, right? That matters. Because if I have a different situation where I have, this red, we haven't used it yet. What if I have a system that has, y'all see this now? Please. Look at what I'm saying. This right here, that's going to be the change. Okay? Now I'm designating not aqueous phase, but in fact, solid phase. Okay? Now, as I do this, right? So what's the big difference in my K equation? What Miriam filled in for us over there, or what who wrote it originally? Somebody wrote it originally, right? Like this one had right? What's going to be the big difference over here? This one, what's going to be different? And why? Perfect. Right. So this one was not a solid, it was aqueous. This one is, in fact, a solid. Right? Therefore, Mary said loud for everybody. So we're just going to do PB2 plus times I minus, still squared, right? No denominator, because it's a solid base, right? Does that make sense to you? I agree. You don't include the solid and you don't include the solvent, like water if we're working in aqueous or in organic, whatever solid you're working in. Don't include those. In this case, the solid is a pure phase, so we're not going to include it. And you can tell that it's one of those because, see, I left this off for a second here. I'm going to fill in this and I'm going to call it KSPs. And what the SP stands for there is solubility products. Okay? Solubility products. These are actually much easier to calculate, right? Because you don't have that whole denominator thing to work with, right? Much easier. Make sense? Yes. Well, I did English, right? Because right? Aqueous means in water. But these will be aqueous here. Say again? Is what just because it's water? It's the reason we left water off of this, and the reason we will also leave water off of this is because it's aqueous phase. But to make sure I'll answer your question correctly, there's a different reason that we leave off the solid. We leave off the solid because it's a different pure phase. We assume that there's some solid still sitting on the bottom of our beaker, right? And then we can just do a solubility product without doing the solid. It only works if there's still solid there. If you run out of it, now you got to go to a whole lot more complicated. That book that hold up, look up, while ago, the analysis we're talking about formation constants. You know what that is. Okay. Okay. Now, be very careful because if I add more lead chloride to this new scenario, right? If Allison puts more lead chloride, what's going to happen in the scenario where we've got solid lead iodide at equilibrium, right? And then we add more, let's say something like lead chloride. Think through what's going to happen for you. Tell me, Kara, what are you thinking?
Wasn't the lead chloride liquid or?
it'll dissolve into PB2 plus aqueous and also to Cl minus. Does that help? Then what? What will that temporarily do to you? Will the Cl do anything? No, it's not any question, right? Will the PB do it? Yes. So that's going to cause this to go up, right? That causes this to go up, causing this to shift. But be very careful, please, because in your solubility product version, you're going to end up with the exact same number. Well, let me say it differently. Let me back up. No, you're not going to end up with the same number. You're going to end up with the same product on this side. They still have to be equal to the KSP. Okay? But what will happen is you will precipitate out more solid mass. You'll get a bigger mound of lead iodide in the beaker, right? But the product, the PB times the I minus squared, has to be rock solid. Okay? Does that make any sense? So adding that PBI, a little shifted, but if I have this, now let's say, what if I'm at equilibrium here, right? And Allison's going to want to mess with me, right? But instead of this, what if he threw more than I? What would happen? Because we're already at our solubility product. And putting more of this in does nothing to not a calculation. So once you reach your solubility, adding more of this, absolutely. Does that make sense? Adding this, that does. But adding this, nope, not in the calculation. Makes sense?
This is only adding part of it.
Yep. And then there's a word for this. It's called the common ion effects. Okay? Yes.
Are you going to use the order equations in software X?
Okay.
Like that will be the last time.
I'm going to keep this as so the worst one, I'll check and make sure. So the worst one on there can in fact be solved with a quadratic. Okay, I do not need to do a cubic. That's I don't need to curve. It's solved. Yes, but not everybody has solver, right? So yes, you can. All right. Beautiful, y'all. I think we're ready. Allison will let. Oh, exam will be 1 week from today, right? And Monday we're gonna do lots of problems, lots of action problems, like ice tables and. Oh, we should probably go back and do some reaction problems too, right? Okay. That's our plan. There it goes again. I don't know what's doing it. Oh, wait, maybe it's catch up. Stop recording. Please. Yes, that's stuff.